تمام.
Hey guys, how are you? Looks like pretty much everybody's here. I finally got your exams graded. Ooh, we've got some fun feedback. I'm gonna say something again. And no feedback. Good. That would be hard. Awesome. All right. So let's see. Any questions about stuff today? Anything you want me to? Your exams are graded. Some of you I just finished, so that's what I've been doing pretty much all day long. So I'm basically totally drained from grading this stuff. If you have any question about it, feel free to ask a question about it. Generally, the grades are pretty good, so that's a good thing. We didn't quite get through everything we were hoping to do last week. I don't know if you guys want to go back and hit some of that or just keep moving forward.
مش دلوقتي خالص لو سمحت.
What was that?
Dr. K. My vote is, okay, I don't know if we're gonna raise hands, but my vote is if we need to cover some stuff from last week that's gonna be on the exam, I'm really down for that. But I know that question number 58 from the homework in chapter 16 has me stumped. It's the only one I'm not able to do. I keep getting lost. I don't know what the Wilson theorem is, and I can't find it in the book.
Okay. Let's see. One thing you can do is Google it, right? So it's a well-known theorem. But yeah, we can look at that. Someone did it for their homework. Who is it that did it for the homework? I just finished looking at it. So I was just looking through these.
What was the question? I'm sorry, people talking. What was the question again? I didn't even hear the question.
Oh, the question was to look at Wilson's theorem. Oh yeah, here it is. Oh, LaDonna, you did it. So
I
LaDonna,
don't look at other people's work. I'm gonna be honest. I just be trying to see what numbers are covered, so I don't hear that, so I can cover when one ain't been covered. That's what I do.
No, I did. I had the question on 30, the Wilson theory, and I have a question on number 14. I think 14 or 15.
Okay. Do you want to explain what you did with Wilson's theorem? I did. You had one question there, which I did answer, and we can talk about that. But do you want to say what you did do? Oh, okay.
Yes, let me pull it up.
Okay.
What question was it? What number? And what discussion I put that in? That was the question. The question.
That's question 58.
Hey, I'm in class right now. Go to the other room, please, because y'all about to drive me crazy.
It's sorry. It's question 58 in chapter 16. Yeah.
Okay, I'm going to it. I'm going to my discussion because I got stuck.
Dr. K.
I'm sorry. My kids, they asking me questions and stuff. Let me go in my room. I'm gonna go in my office. Let me go back to my thing.
Okay, well, let me see. Yeah.
Okay, sorry. So what I was doing is, I'm not sure if you all, like Chris said, people don't look at my thing, but what I'll be trying to do is get concrete examples to start me off. And so I started with 5 times for the in Victoria, and got the 24 with the -1 mod 5. I was trying to start off, but I didn't understand the inverse of the n minus 1, which is, do I supposed to do which are the self-inverse that give us n minus 1? I didn't understand that part right there. That's why I got stuck at right there. I didn't understand none of that I put right there. I was just so confused altogether with this whole problem. I was just reading your answer just a minute ago to find out what do we mean about A equals 1 or A equals -1. And it's not true. So I was just stuck altogether.
So your idea is good. You did, let's see, mod 5, right? So you did that. So you did n equals 5. Let's see, let's go to black here.
And I only understand it because I was doing the concrete with the numbers. But when it's like just the regular, without the numbers, I don't understand what I'm doing. That's why I was just like, okay, so let me just put this in here.
So let's do it maybe like you were doing with the numbers. So we would have like, what is in fact, so with n equals 5, right? In factorial would be like this. I think this is what you're saying. That's in factorial, right?
Wait a minute, let me see. Let me go to my your board. Is your board
on?
Oh,
Dr.
Sorry.
K, can you show your board?
Your board not on.
Yep, I will do that.
Dr. K, I couldn't hear anything at the beginning, so my computer is acted out. So what I missed, because I don't know where we start.
Oh, we haven't really done much
yet. At my
kids. Yeah. we're looking at problem 58 on chapter 16. Crystal asked for it. LaDonna had done it, so I was getting her help to remind me how this goes. And so in this particular case, right, so what we're wanting to show is n minus 1 factorial is equivalent to -1 mod n. And this is supposed to be if and only if n is prime. Right, so that's what's being claimed here. And so LaDonna's suggestion was look at a couple of examples. So let's take n equal 5, right? And so the question is this thing here equal to -1 mod 5? Now what is -1 mod 5?
Is it 3?
4.
4. It's 4, right? So it's always, so minus k is always n minus k, right? So this is the same as saying 1, 2, 3, 4 is equivalent to, n minus 1, so 4 mod 5. Right, so that's what it's saying there, right? And p is prime in this case, so that should be true. So is this true? And then why maybe is it true?
Well, it is true because 5 is prime, and since 5 is prime, what you would do is you get 24. 24 minus 4 times 5, which is 20, with the remainder of 4. So since 4 is the remainder, it's 4 mod 5.
Okay, good. Okay, so it works out. So that's good. Okay, and then maybe what we want to do, maybe what LaDonna was thinking is look for some sort of pattern that helps us figure out what's going on, right? So let's try 6. So that would be like this.
That's what it looks like before.
And so if I'm going to do -1 mod 6, right? -1 now is going to be 5, right? Mod 6. Right, would have to be like that. So is that true?
You just hit me from here.
Oh, turn it back on.
Yes, it is. 25, 30 minus 25 is 5.
So this is, let's see, so this is 12.
You changed that to mod 6, sold up, my bad.
Yeah, this is mod 6 now, yeah. So I think, in fact, for mod 6, what actually happens on this side? And maybe this is a hint at why being prime is important.
That's what I started to say, is that 6 is not a prime, so why would we even try that since we've already set this, established that P has to be prime?
Okay, because this is an if and only if, so we need to know both what happens with prime and not prime, right? We need to know if this holds, then P is prime, and if it doesn't hold, then P is not prime, or one of those directions there, right? So we need both cases, P being prime and P not being prime. And I think here we're sort of seeing what's going on. So 6 is not prime. What is this side over here, mod 6?
20.
Is it 0?
0.
It's 0, right? Because it's got this little copy of 6 in there.
Yeah.
Right? And I think we can see pretty clearly that that's going to be a problem whenever we have a non-prime, right? So if n is equal to PQ, right? So it's not prime. P and Q don't need to be prime, but N is a composite number, right? If we're in that situation, then we're looking at N minus 1 factorial, right? What we're actually going to get along the way is we're going to get one, we're going to get 1, 2, etc. But somewhere up here we're going to get P, and then somewhere up here we're going to get Q. I'm assuming, Q is bigger than P. Maybe they're even the same. Well, yeah, maybe that's actually that's a different question, right? So I guess we have to consider that too. So right now I'm in this case where P is less than Q, right? So suppose I'm in a case like that. So N is composite, P is less than Q, and we have something like that. And then I go on up and I have N minus 1. All right, what's going to happen here is I'm going to get 0, right? Mod N, right? Because when I put those two pieces together and multiply them, I'm going to get 0, right? So that's going to happen in the case that N is composite and it has, it can be factored into two numbers where one is bigger than the other, right? So we're in that sort of case, right? So we still have another case there where N maybe is of the form M squared, right? So maybe this is a different sort of situation. What happens there? I'm not really sure. I'm sort of not looking at my answers either, right? So we'll have an M, right? I mean, that'll be along the way, right? We'll keep going. We'll get up to N minus 1, which is M squared minus 1, right? And I guess the question is, can this be equal to minus 1? So that would be the same as M squared minus 1. Whoops. Mod N, so M squared here in this case, right? So if we're in that kind of situation. Notice, by the way, that these we can also, if this were true, right, this is the thing we want to show has to fail, right, in this case, because this is not prime, this is composite, right, in this case. Then we could cancel out those two things right there and really just have, we could go up to like M squared minus 2, and is that equal to 1, right, mod M squared.
Could you repeat that, Doc? You lost me for just a second. It's like you moved in my head.
Yeah, because we're stopping here at N minus 1, right? And we're saying that's equal to N minus 1. This side, that's the same as minus 1 mod N, right? So I mean, it's equivalent to just saying, so let me rewrite so if we look at 1 to, N minus 1, we're taking the product of all these things. In fact, let me do N minus 2, N minus 1, right?
I follow.
So this is N minus 1 factorial. And we're saying this is equivalent to minus 1 mod N, right? But minus 1 mod N is the same as N minus 1 mod N, right? So those are the same. And we could just cancel those things, right? And say this is, so another way of saying this is we have this to 1 mod N, right? So that would be another way of saying this.
So would that be N minus 2 factorial is equivalent to 1?
Well, it would be N minus 2 factorial. It's the product of everything up to N minus 2. So yeah, that would be N minus 2 factorial. All right. So yeah, I mean, that's a point too, right? Saying N minus 2 factorial is equivalent to 1 mod N is exactly the same as saying N minus 1 factorial is equivalent to N minus 1 mod N. And that's equivalent to saying equal to minus 1 mod N, right? So we have that sort of situation. And yeah, I'm still sort of, we're sort of sitting here on this M squared. So that's where I'm getting stuck at the moment. So what we have is we have that if N is equal to PQ, so if it's composite like that, where these are not the same, right? So I can assume P is less than Q. Then we know that this doesn't happen, right? So that's what we have. Go ahead.
Was something going to say?
Okay. So the only case that we haven't covered in the composite case is the case M squared. So somehow or other we need to figure that one out. All right. But what about, so let's think now about the case where we have a prime, and maybe we can think about what's a small version of m squared. Let's do an example. Let's keep doing LaDonna's idea. So like 9, right? So it'd be like 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8. That's n minus 1 factorial, right? We're doing mod 9, right? So this is the case we're in here. So what happens in this case?
We're establishing that m squared is equal to 9. Is that what we're saying, though? Are we defining m squared as 9?
No, remember. So let's keep in mind. Don't forget what we're proving. We're trying to prove Wilson's theorem says n minus 1 factorial is equivalent to minus 1 mod n. Whoops, mod n. If and only if n is prime. Right. So I mean the point is this is an if and only if. I mean it's got these two directions, right? And what I'm considering now is the cases where n is not primed, and I want to show this fails, right? That's what I'm trying to do. All right. So that would be, so I mean, okay, we can work out the logic, right? So if n is not prime, then not that, right? Right, that's what I'm trying to work out now, sort of by looking at examples. So when we're in the case that n is a composite of two numbers which are not the same, we're done, right? So the case we sort of have left over here is the case where we've got a composite where the two numbers are the same, right? So that's the sort of situation we're in here, right? And we're trying to ask what happens in that case, right? So this case is, you know, n equals 9, which is 3 squared, right? So what's happening in this case? Did you do anything with that case, LaDonna? Are you there, LaDonna?
I'm talking, but I ain't have my mic on. No, I didn't do anything with the case. I just stopped right there because I never did understand why the 1 and n minus 1. I'm trying to follow along with you right now with why it's 1 and n minus 1 are not inverse of each other. So I was just confused on that right there. So that's why I stopped that. I ain't do anything else besides that little part right there.
Okay. Let's see. So let's see. I'm not just seeing an obvious thing here. I mean, I may have to look at my notes too, just to see what I did. Let's see what happens when we are prime, right? So that's the other option, right? So when P is prime, let's think about that. Maybe someone else will think about how to finish this. When P is prime, what happens is we have like this 1 times 2 times. In fact, okay, sorry. I want to stick with what you said, LaDonna, and stick with examples, right? So, sorry, was someone going to say something?
It might not be right. It was just when you were doing the 9 example just a second ago before you started to move on, could you say that 6 is 3 times 2, and then you'll get the 2 copies of 3, which means that that you'll get that remainder of 0? Does that make sense?
6 is equal to 3 times 2.
And then so you'll have 2 copies of the 3.
That's a good idea. Good. Okay, so yeah, that's a good idea. So if I'm looking at an m squared, let's see, what is that actually saying? It's saying that there's something less than this thing, right? So it's saying that. So you're saying that like.
But I'm lost. Where did he get 3 times 3? The 3 plus 3 from the factorial. Factorial is multiplication, so I'm lost.
Yeah, it's this. Well, I mean that's the multiplication, right? So n is 9. So this is 9 minus 1 factorial is that, right? Okay, so but in this case we're at m. So 3. So we do. So you're right. So 2 times 3 is less than m, right? So 2 times 3 is less than m. Less than n, right? Less than n, right? And 3 is less than n. No, I think this works. Okay, let me see if I can just write it out, right? So if I'm looking at m squared, right, I want to show that this, what we're trying to show is that this does not satisfy this. Where n is equal to m squared. And I don't quite have this right. I need it like this. Right. So that's what we're in this case where we are a composite, but we're a perfect square, right? That's the case we're in. Okay. And we want to show that this doesn't happen, right? And I think what you said works, right? So smaller than this would be m would be less than m squared minus 1. That's certainly true, right? And then what else can we do? I guess we can just say 2m, right, is less than m squared minus 1. And maybe we're in this weird case where maybe m is 2, right? I'm gonna sort of, we can keep wiggling down to edge cases so we get down to 2 squared, right? So that's like, but we can deal with 2 squared all by itself if we want to, right? But I can assume that 2m is less than m squared minus 1, and I can assume that m is less than m squared minus 1, right? So that means on this side, somewhere in this big product, I have 2 times m squared, right? So that was Jordan's idea, right? And so this is going to become 0, right? So again, in this case, where n is equal to m squared, what we're actually getting is 0 here, not minus 1, right? Does that make sense?
Yes.
Should we try it with I mean, so I did it with 3 and I did it with m. We can do it with 5, right? So, oh, not 5, sorry, not 5. I can do it with like 5 squared, right? So that's 25, right? So along the way, when you're taking 5 squared minus 1 factorial, right? Among the things you'll have here, 1 times 2 times 3 times 4 times 5, you'll have that, right? And so then you're going to keep going and you're going to have 10, right? Which is 2 times 5. And you're going to keep going up to 24, right? When you're taking that factorial, right? But when you take this and this, it's going to have a copy of 5 squared in it, right? So this will equal to 0 mod 5 squared. Right? Good. Okay, so we've actually gotten is that if we have any composite number, right? So we've actually shown that if n is composite, then n minus 1 factorial is equal to 0 mod n, which is not minus 1 mod n, right? Okay, so now we want to deal with prime. Okay, and I guess this is where something else happens. So now we have a prime, like 1 times 2 times 3 times 4. This was LaDonna's original example. So we is equal to minus 1 mod 5, right? This is what we want to show. I mean, we did argue that, right? Just sort of in the air. We argued that that was true. But now why in general would that be true, right? Just sort of looking at this, or maybe let's take one more, like 1 times 2 times 3 times 4 times 5 times 6 should equal to minus 1 mod 7, right? That would be another example.
I know why. Because
Why is
if
that?
we go 4, if we said 4 minus 5 and we subtract it going the other way on the number line, we come up with negative 1 mod 5. So that's why that's true. And 6 minus 7 is going to give us negative 1.
That's true. Yeah. So that's something like what I was doing a minute. So we could change this. So, and I think what you're saying is this. So over here, so the minus 1 could be replaced by a 4, right? And the minus 1 here could be replaced by 6, right?
Yes.
So that would turn these two things into this. 1 times 2 times 3 is equal to 1 mod 5. So let's see, why is that true, right? So this is equivalent, right? This is 1 times 2 times 3 times 4 times 5 is equivalent to 1 mod 7, right? Or, generalizing, this would be saying that p minus 2 factorial is equivalent to 1 mod p.
Correct.
Right? So if we can show that, that's good. Now, do we kind of see why that might be true here? Like, things are sort of coming up in pairs here, right? Like, first of all, there's a 1, right? So I could simplify this by also getting rid of the 1, right? Now, if I get rid of the 1, what's the rest of the stuff I have here? Remember, I'm working here in Z5. What can you say about 2 and 3 in Z5?
They're relatively prime.
Well, they're relatively prime. I don't know about in Z5. We haven't thought about that yet, but in Z5, algebraically, 2 and 5 2 times 5 is 3, which is 1, right? So 2 and 3 are inverses, right? Okay. So everything has an inverse, right? Mod P, right? Everything has an inverse. So they come in pairs. They come in inverse pairs, right? So all these pairs here have to, whoops, I did not mean to do that. All these pairs here have to come with an inverse paired with it, right? So in mod 7, what is the inverse of 2 mod 7?
The 4.
4, right? So my little, there's a pair. And what can we say about 3 and 5 mod 7?
They're also
They're inverses.
inverses.
They're inverses, right? Okay, so these things pair up in pairs of things that are inverses. So those all multiply together to give me 1, right? Because I could rewrite this as like 2 times 3 times 2 inverse times 3 inverse, right? Sort of like that. Right? And that's going to happen with any prime, right? So with any prime, when I do it, think of it like this. I have 1 times, 2 up to, p minus 2, right? And we're trying to show that is equal to 1 mod p. Okay. Well, we knock off that guy right there, that 1, right? And then what happens along the way is we have everything paired up in inverses, right? So everything has an inverse to pair with it, right? So all of these things have an inverse pair that go along with it. Right? We can do one more. You want to do like we did 5, 7. What's the next prime?
11.
11.
So the thing we're trying to prove is 11 minus 1 factorial, right, equals minus 1, right? This is for prime p, so mod 11, right? And then I'm just going to go through and I'll make the changes we've made already. So this is like 1 times 2 times, dot, 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 times 10, right, is equal to, and now minus 1 is the same as 11 minus 1. So that's 10 mod 11. So we're sort of in that case, right? And then I can knock off the 10 there, right? So we get 1 times 2 times 9, right? So that's the p minus 2, right, would be 9, is equal to 1 mod 11, right? So that's what I would need to show. And then I can sort of knock off that 1 there, right? And now everything's is in pairs, right? So I have 2 times 3 times 5 times 6 times 7 times 8 times 9 is equal to 1 mod 11, right? Now, of course, I want an argument that works regardless of what the prime is, right? So we need to say, well, everything here has an inverse, right? So, I mean, in this case, we can figure out what it is. What's the inverse of 2 mod 11?
6.
Because 6 times 2 is 12. Yeah, so this is like 2. This is going to be 2 inverse. Okay, good. What's the inverse of 3 mod 11?
4.
Because 3 times 4 is 12. Yeah, what did I do with 4? Where did that go? Right. This is 3 and then 3 inverse, right? Now what's the inverse of 5 mod 11? A 9, right?
5, yeah.
Right. So 9 will become 5 inverse. What am I up to? So that's 6, 7. What's the inverse of 7 mod 11? I guess it better be 8. What's 7 times 8? Yeah, 56, right? It's 1, right? So 7 inverse, right? So you see they're coming in inverse pairs, right? And so when you sort of pair these things up, the 2 and the 2 inverse and the 7 and the 7 inverse and the 5 and the 5 inverse, 3 and the 3 inverse, right? Then you just have 1 times 1 times 1 times 1 times 1, right? So it's equal to 1 mod 11.
So Doc, if I can ask a clarifying question, instead of writing 6, you wrote 3 inverse, 3 negative 1 so that it was 2 times the inverses. Instead of writing the actual number of the inverse, you wrote it as an inverse with the inverse exponent.
Yeah, I'm trying to make it clear that when you remove, so I'm trying to make it clear. So now the goal for you, right, to finish up the problem is when we have a prime p prime, right? So what we're trying to show is that p minus 1 factorial is equal to -1 mod P, right? Because that's what we were trying to show, right? And so we did a couple of little things to finagle this. We changed this to P. So again, if we just sort of write it out, right, it's 1, 2, dot, 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 P minus 2 times P minus 1. And then the -1 can be replaced by P minus 1 mod P, right? Because -1 is the same as P minus 1, right? Okay, so we can cancel out these P minus 1s, right? So now this thing is equivalent to saying 1 times 2 all the way up to P minus 2 is equivalent to 1 mod P, right? But then we can cancel out that 1 because multiplying by 1 on both sides doesn't matter. So now we have 2 times dot, 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 times P minus 2 is equal to 1 mod P, right? So we need to show that in general. Now we need an argument where we don't have to look at specific numbers, right? But the point is every number, so there's an even number of numbers there, and every one of them has an inverse paired with it, right? So they come in inverse pairs. So when we group those things in pairs, we're going to get, 1 times 1 times 1 times 1, right? So we'll just get 1 at the end, mod P, right? That's the idea.
So for the answer for the n equals 11, the answer is going to be 1 mod 11, and that's it. It's going to have another element.
No, it'll just be 1. Now remember, this is what we're trying to show, right?
Okay.
We're again sort of working backwards, right? We need to remember what we're doing. So we're trying to show 11 minus 1 factorial equals -1 mod 11. That's what we were trying to show, right? And I did the same sort of finagling here to change it, right? So I guess I have it all still written here, right? I mean, I'll just, so what is 11 minus 1 factorial? It's 10 factorial equals -1 mod 11, right? But what is -1 in mod 11 is 10, right? So this is 10 factorial equals, so I'm writing it a little bit differently, 10 mod 11, right? So we can cancel out the 10, and so we end up with 9 factorial. Again, we can't forget what we're doing along the way, right? It's equal to 1 mod 11, right? So now I just canceled out the 10, right? And the only other thing I do is I pull off the 1 from the front, right? So that I end up, so I expand this to just say 2 times 3 times 4 times 5 times 6 times 7 times 8 is equal to 1 mod 11. Remember, we don't know this yet. We're trying to show this, right? But then what we did is we paired those up in pairs to see that, everything has its inverse pair, right? And so those things pair up in such a way that when we multiply that all out, we get 1, right? Because in the end, we just have 1 times 1 times 1 times 1, right?
And then is that just a property that every element has an inverse?
That's true, right? In ZP, for P of prime, right? Every element has a multiplicative inverse, right? And why is that? What is this, like from week 1 of the class? What theorem is it that gives us that everything has an inverse? Bezo's theorem, right? Bezo's theorem, right? Because if we take A and B, in ZP, right? Then what do we have is sorry, not that. We take A and ZP, right? Then we have the GCD of A and P is equal to 1, right? Because P is prime. That's the point, right? And so then we know that we have some X and Y such that AX plus PY is equal to 1, right? And then if I take mod P on both sides, I get AX equals 1 mod P, right? But that tells me that X is equal to A inverse mod P, right? I mean, so this was our original proof that in ZP is always, everything has a multiplicative inverse, right? Do we have another proof that ZP has that everything in ZP has a multiplicative inverse? So before I leave this problem, because my next question is sort of going into some of today's stuff too, is there one little subtle thing that I might be missing when I say pair these things up, and they obviously pair up and you just get 1, right? Because everything pairs with its mate, right? You multiply those things together and you get 1.
I don't know if I'm right, but in chapter 17, there's a thing that we did when we were creating fields and where we were checking fields, and you had to make sure that the leading coefficient, it didn't divide into, and that p squared or n squared didn't go into the constant. And this kind of reminded me of that. So I don't know.
So there is something with a square here, yeah, because a potential problem here is I've got my q less than p, and I know q has an inverse, right? So I'm saying take q and pair it up with whatever q inverse is, right?
Mm-hmm.
And right now I'm claiming that that uses up 2 elements, right? Because I'm saying pair these things up in pairs, right? So the issue is it true maybe that q squared equals 1 mod p? Like, does it have to pair up with something else? Or could it be that, you know, q is its own inverse mod p for some q, right? So that could be a problem with this argument, right? So there's all these, like, when you do these proofs, and LaDon, I like the way you did it because you start with some examples, right? And you try to sort of get rid of these things called edge cases as you go, right? So it's like we had the composite number PQ where P and Q are different. That was easy to show, right? Then I have to deal with composite number N, which is M squared, right? That was kind of an edge case. And if you really look carefully at what we did, I was sort of assuming that the number was bigger than 2, right? So we still have this sort of edge case 2 times 2, right? And so here in this prime thing, we have this issue where maybe it's the case that q squared is equal to 1 mod p. Now, why can't this be true? This is good for today's, and I think, LaDonna, this is actually the question I answered.
That's the question I had right there. That why couldn't it just be the PQ equals 1? That's what I was like. I don't know. I just gave up.
Yeah, so this is important for the current. All this is important for the current material. But so far, what we've been doing is almost still number theory, right? But now we're going to do something very field related. Why is it the case in ZP that the only solutions to x squared equals 1 are plus and minus 1? Why can't there be other solutions, right? Some other p or something. Why can't there be something else? So here's, suppose we had, so what's another way of saying this? We want to start thinking about polynomials, right? So we also have this polynomial x squared minus 1. So this would be in like zp of x, right? Okay, and what do we know about this? So we know that, we know we can do our usual algebra and say this is x minus 1 times x plus 1, right?
So that's the basic, when you get to x squared equals 1 from that x squared minus 1 to set it equal to 0, isn't that the basic? I learned that this weekend. I'm looking for that word.
I'm not sure what you're saying, but it's definitely true that 1 and minus 1 are both roots of this, right? They both satisfy this, right? They both, if I put in 1 there, I get 0. If I put in minus 1, I get 0.
It's the basic field, right? No, that's not the basic field. It's the P. No, that's not the P. It is. I'm getting close. It's the reduction rule. No, it's not the.
I'm not sure what you're calling the reduction rule, but maybe. But I want to say, suppose there's another root, right? We want to show those are the only roots, right? Suppose something else is a root. Suppose f of a is equal to 0, right? What do I know about this polynomial if f of a is equal to 0? I guess there actually this isn't so hard, right? What is f of a?
Maximal?
F of a. Well, no, there's something about maximal ideals here because we're in a field, right? But that's sort of not at play right now. But if I put in a here, I get a minus 1 times a plus 1, right? And that's equal to 0, right? Because I'm assuming f of a is equal to 0, right? This is like basic high school algebra now, right? I'm saying take an a, right? We're plugging it into the polynomial. So, evaluating this polynomial at a, I get a minus 1 times a plus 1, right? And it's equal to 0. Everyone clear there, right? Okay. But what do I know about one of these things and why? So I've got a product which is equal to 0.
So one of them has to be 0.
Zero.
And,
Right.
and why is that?
Right.
Because their product is 0.
Well, it's certainly not true in say
it's the
Z6,
We look
right?
non-zero.
for like this is the intersect to like the x-axis. So these the points that intersect the
No,
x-axis.
no. Don't think
This is-
graphing here. Think algebra.
Is
In
this the
Z6
non-zero that we
in
did last
Z
week?
in Z6, I have 2 times 3 equals 0. So it's not true that two things multiplying together give me 0.
Zero
It
divisor.
means that one of them is 0. But here I'm in ZP where P is a prime. So in particular, P is a field, right? Can fields have any 0 divisors?
Every element is a unit or a zero divisor.
No,
In a
since it's a
field,
field, they don't have any zero divisors.
yeah, since it's a field, there's no 0. It's it's an integral domain, right? So the point is, since ZP is an integral domain, and we don't even need field here, we're just integral domain, one of these two things has to be 0, right? And if A minus 1 is 0, then it means A equals 0, right? If A plus 1 equals 0, then it means A equals minus 1. I'm sorry, not A equals 0, A equals 1, right? So here I took an arbitrary root, right? And using the fact that we're in an integral domain, we can see that we can just solve for A then, that A has to be 1 or minus 1. So those are the only two possible roots there, right? So the only thing that squares to give me 1 is minus 1 and 1, right? So when I'm looking at my primes, right, I'm trying to prove this thing, times P minus 2 is equal to, 1 mod P. And I've already sort of gotten rid of that 1 in the front. None of those things satisfy K squared as 1. That doesn't happen there, right? So they do really come in pairs, right? And so that's important for the proof we did above. Okay,
Dr. K,
so
how do we determine the difference between the there's the PID and the integral domain? I rewatched that video over and over again, and I still was unable to distinguish the difference between it.
Yep. So that's if I'm going to lecture on PIDs, I need to get into that, but that's a slightly different thing. Right now, let me just point out ZP. I mean, here we're doing something a little bit strange, right? ZP is a field for P prime. We actually know this ahead of time, right? And this is because of Bezout, right? We just saw that a minute ago again, right? So we've seen that throughout the class, right? We've seen that we have inverses. Is it clear why when we in a field, I mean, the definition of field is an integral domain with inverses, but is it clear why when we're in a field, you can't have 0 divisors? Right? I mean, if we're in a field and we have A times B equals 0, right? So I'm in a field, right? So I have inverses, right? So what do I know? What can I do here?
Is it either A or B or 0?
I mean, yeah. So I mean, I can say, suppose A isn't 0, right? Then I know I have an inverse for A, right? Because the field, everything that's not 0 has an inverse, right? So then I could multiply A minus 1 times AB is 0, but that would imply B is 0, right? So since we have inverses, we can just cancel, right? And get that the other thing has to be 0, right? So no unit can ever be a 0 divisor, right? I mean, that's more generally what we're showing here. If we're in any ring, maybe a ring with 0 divisors, right? The things that are units can't be 0 divisors, right? On the other hand, we know from something we did last time that if we're in a finite integral domain, right, then in fact that's already a field because we showed that everything was either a unit or a 0 divisor, right? So if we're in an integral domain, finite integral domain with no 0 divisors, then everything is a unit, and so it's a field, right? So I mean, we're sort of getting that from two different directions here, right? But really, in this case, we knew field first, coming from Bezout's theorem, right? Okay. So this is a good problem to talk about because it sort of leads through a bunch of stuff, right? But Mel, maybe it is a good time to sort of get into the meat of PIDs and Euclidean domains and all that stuff a little bit, right? So let's kind of delve into this some, right? And I will let me pull that over there and let me pull my notes. I'm not going to do everything in these notes because there's an awful lot of stuff in these notes. Pull that down. Come on, thing.
Yeah, right there.
Let me say a little bit about this. I mean, I just can't skip too much here because I'm going to have to use it, right? And so just like we had groups, let me get your, sorry, I've lost my picture of you guys. Let me get it back up there so I can see you. Just like when you had groups, right? We've talked about the subgroup generated by a subset, right? And there were kind of two ways of doing it. So, I'm going to say recall when we were in the realm of groups, right? And I have some S, which is a subset of G, a group, right? And we could define the subgroup generated by S, right? And there were two definitions. One was the intersection of all the H's such that S is contained in H, and this is a subgroup of G, right? And you proved that that was a subgroup, right? And you proved that it's the smallest subgroup containing S, right? So we say it's the subgroup generated by S, right? Now this was sort of a useless notion because you don't know all the possible subgroups containing S, right? That's potentially a huge set of things, right? A more useful example was, a more useful definition is this is the set of all words. So things like this, S1, Sn, where Si is contained in S, right? So you think of S as an alphabet and you think of this as a word in that alphabet, right? You just look at all those strings from S, right? Well, that forms a group, and you prove that, right? So if I multiply two of these strings together, I get another string because you're basically just sitting them next to each other, right? If I look at an inverse, I get a string in here because what do? I flip the OR and put inverses on top of everything, right? So we know that. What else? I guess I do need to allow myself some, at least a plus or minus one up here, so that I throw in inverses, right? I need to allow inverses as well, right? Okay, so this is sort of a bottom-up way of defining what the subgroup generated by S is, right? This is a top-down way, right? I'm taking the intersection of everything bigger. Here I'm sort of filling it in from below by just putting all these sort of words together. Does that make sense? Sort of working from underneath and working from on top to define these things, right? Is that clear? I want to see some like thumbs up or shakes or something. Okay. Because you need to know this old stuff.
A string gives you another string, and that's what you just said.
Right, yeah. Because if I take two of these things together, right, that's another string in here, right? Now I may be able to do other things with them, right? I may be able to actually multiply them together and cancel and stuff like that. Those would be called reduced words. So I could reduce, like if I run in along the way, if I run into an S1 inverse, right, I can just sort of get rid of it, right? Because that's an E, right? So I can throw that part away, right? So you can reduce them, right? And you can also, if you want, add powers. So you can look at S1 to the K1, and stuff like that, right? So this would just be like K1 mini S1s, things like that. Okay, we need the same sort of construction, but for rings now, right? So I want to look at now rings generated by S. So now we're in the ring setting, right? So I'm taking an S subset of rings. What do I need to generate the ring? Well, I need to generate a subgroup, among other things, right? So I'm still going to need all these words, right? So I'm still going to need to add. So remember, the subgroup part of here is the addition part, right? But I'm also going to need the multiplication. I'm going to need sort of multiplicative versions of the words, right? So again, you could define S as the intersection, of all R prime, right, where S is contained in R prime, and R prime is a subring. So that's the top-down version, right? Right? Or you can say, well, what I'm going to do instead is I'm going to look at the summation, over whatever. It's going to be a finite sum. I don't know what the indexing is going to be, of a bunch of products, right? Let's say Li. So now those things, right? Where these Sj's are in S, right? So I need to close under products and sums, right? So it's a little bit more confusing, right? But I need all that stuff, okay, to do this. We don't do too much with generated rings, but we do a lot of stuff with generated ideals. Okay, so that's really sort of where I want to go now. And I'm going to use the same notation, unfortunately, but almost always in class when we're looking at this notion, I'm going to be talking about the ideal generated by some set. Okay. So let's sort of look at those cases. So now I've got an S, which is a subset of R, right? And I want to look at the ideal. Let's think about this. Let's actually work through this proof. The ideal generated by S, right? So, and unfortunately, I'm going to use the same notation because, I mean, I tried two different notations in my notes. I try using this instead, but too many things use that notation. So it's one of these things where you have a notation which is being used over and over and over for lots of different things. And you really have to keep in your head what the context is, right? So if you're generating ideals, you need to think about generating ideals. If you're generating groups, you need to think about how you generate groups, right? If you're generating rings, you need to think about how you generate rings, right? If you're generating vector spaces, you got to think about how you generate vector. I mean, you've got all these different sort of structures, right? Same kind of ideas in lots of them. You can take this top-down approach, intersect everything bigger, right? And that gives you one of these things. Or you can take this bottom-up approach where you construct the elements inside there, right? So that's what I want to do here. So first of all, if I just define the intersection for I contained in R, I an ideal, and S contained in I, right? Do I get an ideal? Right. So that's the question. Does this give me an ideal? Right. If it does give me an ideal, then it's clearly going to be the smallest ideal containing S, right? Because whatever the ideal is, it definitely contains S because of that. And if there's any smaller one, well, it's in the set, so I'm intersecting over it, right? So this is definitely going to give me the smallest ideal containing S. Okay, so is this intersection an ideal? What do I need to show that it's an ideal? So what properties do you need for in order to show that this thing is giving me an ideal, what properties do I need it to have?
Closure?
So
addition, multiplication, and identity.
Yeah, so there's a couple of ways of saying it, right? We need to know that the generated thing is a subgroup, right? So that was one thing we needed. So that would be closure under the additive part, right? We need to know that it's a and the negative part, right? The minus part, right? So you need both of those for subgroup. You need that it's non-empty, but that's trivial because we're assuming S is non-empty and S is contained in all these things. And then you also need closure. So an ideal was also a subring, right? So you also need closure under the multiplication. But actually, you need something stronger for ideals, right? So what we really need in order to show this is we need to show that R times this thing S, right, is contained in this thing S, right? We need to show that S times this thing R. So it's stronger than just closure under multiplication, right? Because we need this left and right closure by multiplying by anything in R, right? Remember, in some sense, this is going to be playing the role of 0 when we mod out, right? So this is like saying anything times 0 is 0. 0 times anything is 0, right? That's kind of the idea there, right? So we need that kind of stuff, right? So is this true? So if I take an R, which is an R, right, and I take something in here, I take an S, which is in this, let me not call it S, let me call it A, right? So an A, which is in this S, right? Is it true that RA is also in this S? Because that's what we need to show. I need to show that R times anything in R times anything in this S, right, is going to again be in that S.
Yes, right? It's true. If
okay,
R
and why
is
is
in
it
S and A is in S, then if you multiply R times A, you're still going to be inside S.
Well, no, R is in R, right? R is anything in R. Yeah.
But isn't R a subset of S?
No, S is a subset of R. We're creating ideals of R, right? So R is bigger than the ideals. R is bigger than the set S, right?
Okay, so I'm reading the notation wrong then, because that looks like yeah, I'm reading it wrong.
This is a product, right? This is saying anything in R times anything in this thing is contained inside of this thing. And I'm just going to call it the ideal generated by S, although we're in the middle of proving that it's an ideal, right? I need to show that anything in this ideal generated by S times R is contained in S, right? This is part of what an ideal had to satisfy, right? It has to satisfy R, I is contained in I, and IR is contained in I, right? And it has to be, you know, and it had to be like a sub ring or a subgroup, whatever you want to say, but I is a subgroup.
Isn't it that because A is in S and S is in R, if we do R times A, it would have to be in.
That's what I said, I thought.
Well,
But
no,
that's
because R
working
is in R,
backwards.
not as in S, right?
I see
But so
my
A,
mistake.
no, you don't have a mistake. So A is in S, right? But that implies A is in I for all I containing S, right? Because that's what I'm doing. I'm intersecting all the ideals containing S, right? But this is an ideal, right? So in particular, Ri is contained in I, right? So this implies Ra is in I for all I containing S. This is the key point right there, right? Because I is an ideal, if I multiply by anything in the ring, we stay inside the ideal, right? Okay, but this implies that Ra is in S because that's the definition of S, right? Same thing if I multiply on the right, right? It's the same argument. If I have A is in S, A times R is in I for all I in containing S, right? So A times R is in S, right? So both of those are true, right?
So you're
So
saying S is in the ideal?
I want
Is
to
that
make
what's
sure
that-
we
when
understand.
you
I want to
said
make sure we
S
understand what we're doing
contains-
here, right? So R is a ring.
Right.
S is a subset of the ring. That's all we know. Subset of R, right? This thing here is the intersection of all ideals containing S. So we're intersecting all the ideals containing S, right? And the claim is that this thing is then an ideal. So the claim is that S is an ideal. How do you show something's an ideal? You have to show S is a subgroup. So the additive part is a subgroup. That was one part you had to show. And you had to show that R times S is contained in S, sorry. And you had to show that S times R is contained in S. Those are the three properties for being an ideal, right? That's what it means to be an ideal, for S to be an ideal, right? So that's what we have to show, right? And so what I just went through the proof of was that this one is true, right? The proof of the other one is exactly the same. The fact that it's a subgroup is exactly like what you've done before. So I'm sort of not doing that, right? So the upshot is if I take the intersection of ideals containing S, I get an ideal containing S, right? That's the upshot. I get the smallest ideal containing S because I'm intersecting all of them, right? That's the top-down definition of the ideal generated by S, right? Now we need the bottom-up definition of the ideal generated by S, right? And so what do we get there? And now I'm going to restrict to a special case, right? Now I've got all these others in the notes, right? So I've got the case where R doesn't have a unity, R has a unity, R is commutative and has a unity, right? Okay, so things get less and less complicated the more structure you have. Okay, so I'm going to go to the case. I'm just going to look at the case where R, so I'm going to restrict to this case where R is commutative. Remember when we say R is commutative, we mean the multiplication part is commutative, right? The additive part is always commutative. And unitary, so it has an identity. So we're going to be in that case, okay? So in that case, what I claim is that this S we're generating is really just the sum I equals 1 to n, so arbitrary sums of AI, where AI is an element of RS. Okay, or if you like, I could say this is the sum I equals 1 to n of, say, RISI, right, where RI is an R and SI is an S. Again, we're having to take all these sums just like we did for groups, right? To get the group generated by something, we had to, and we're doing the additive group, we have to add in all the pieces, right? So those are the words, except now we're not doing multiplicative, we're doing adding, additive notation, right? So how do we prove this? So all we really need to do is show that S is contained here, right? So that S is contained here. So why is that? Remember, I'm assuming it's commutative with a unit, right? So why is S contained in this set? If S is an element of S, do I know that S is writable as one of these things?
Yes.
So how would I write it as one of those things?
SI is S.
SI is S, so 1 times S, right?
Yes.
And I'm using the fact that we have a unit, right? So yeah,
Yes.
so this is an element of this set, right? So good, right? So good. So S is contained there. Is it true that RS is contained in S, right? So now what I need to do is I need to take an arbitrary thing from here. So let, A be in here. So what does this A look like? So A equals some summation of things that look like this. These are like linear combinations, right? It should remind you of linear algebra in some sense, right? Where Ri is an R and Si is an S, right? And now I'm taking an R in R, right? And I need to show that RA is in S, right? But what is RA? So RA is just R times that thing there. Right? And we can distribute, right? So this is the same as summation I equals 1 to k R times Ri times Si, right? And that's a thing in R, right? And so this thing is in S, right? Okay, so we have that containment. We don't need to do the containment in the other direction because in this case, I'm assuming commutativity, right? So I really only need, when you're in a commutative ring, I only need to show that IR is contained in I or RI is contained in I. I really need one of those things. So I'm in a commutative ring, right? Because I don't have to worry about the order. Okay. Good. Okay, so as a very special case, when I take S element of R, what is the ideal generated by the singleton S? Right, so we tend to denote that as this, right? So now this is not a set, it's just an element now. So according to our definition, what is it? Well, it's a set of all I equal 1 to k Ri times something in here, which is just S, right? So we're looking at sums of things like that, but can I just factor the S out of there? Oops. Right, come down here, right? This is just summation I equals 1 to k Ri times S, right?
Okay. I saw
So
that.
this is really just R times the single thing S, right? Everything in R times S. Okay. So when I generate from a single element, and I'm in the case where I'm commutative with a unit, right? then the ideal generated by a single element S is literally just the product of R times S, and it doesn't matter what order I do it in. It could be S times R. Okay.
Because it's commutative.
Well, yeah, because it's commutative and it has unity, right? And these are the principal ideals. Okay. And if you go back to the general case where now I've got a set, you can think of this as sort of the infinite sum of these principal ideals. Right. So you can think of it as like, and let me, so, okay, infinite sum, maybe we don't really need, but let's do it with a finite number of things. Suppose I have finitely many things. So I'm generating the principal ideal from those finitely many things, right? That's the same as S1R plus S2R plus SKR, right? Where all this means is the sums of S1 times something in R plus S2 times something in R, etc., right? So if I'm generating from a finite number of elements, it's the same as just adding together those finitely many principal ideals, right? So we can see we can generate certain ideals from principal ideals. I guess one thing I didn't do, which is in the notes, and it's in the notes because I need it here, I need to define what I plus j is, right? But it turns out I plus j is just the set of all A plus B, where A is in I and B is in j, right? And it's important here to know that this is an ideal, right? So, check, I'm going to say you check, this is an ideal. Whoops. And in fact, it's actually, I plus j is actually the smallest ideal you build by taking the union of I and j, right? So that's another way you could define it that way too. Okay. But that makes perfectly good sense. So now, this is a principal ideal, that's a principal ideal. I'm taking the sums of principal ideals, right? So if I'm generating an ideal from finitely many things, then it's going to be the sum of the principal ideals, right? Like that. Okay. Unlike with groups, we're going to use this a lot. I mean, we treat the ideals almost like they were numbers, right? And so we do a lot of stuff with ideals. Let's see, just for completeness, let me just put in the last thing. If I have two ideals, then the product of two ideals is not just this. It's not just the set of all A, B, such that A is in I and B is in J. The reason is because there's no reason that's closed under addition. Right? So when we take products of ideals, what it really is it's the smallest ideal generated by those things. So it's really that, where now this is just the set theoretic version, right? Where I'm just taking the products of things in there. And if you want to spell it out more, it's the set of sums where AI, BI, I goes from 1 to K. Again, all these sums are finite, where AI is from I and BI is from J. Okay. And what's really important here is that I, Ri is contained in I, right? A JR, again, I have commutativity, so either way, right, is contained in J, right? So what you have to be a little bit careful here about is that IJ is actually contained in I intersect J. Okay, but it's completely possible for this ideal to be strictly contained in the intersection. Okay, so that's just something to keep in mind. Okay. Let's
Can
take
you
some
say that again and explain why it's different? Why it's contained in the intersection, but it's that point where they might intersect. It could be the null. It's not the null set, but it would be one point, or it just doesn't. It's not equivalent. I got lost.
Yeah, let's look at an example. So let's take R to be Z. mean, I guess, see, so first of all, why is it true? It's because those two things have to hold. This is a J, right? So J times R is contained in I, I times R is contained in I, J times R is contained in J. So in particular, I times J is contained in both I and J, right? Because of these two things, right? So I times J is contained in both of those. They don't have to be the same though. Okay, and generally they won't be the same. So if I take R to be Z, let's see, and I take, let's say I to be 2Z. So notice that now this is literally the principal ideal generated by 2, right? Using the notation from above, right? Okay, and I take J to be 6Z. Okay, what is I intersect J? So it's things that are in both. So it means that A has to be equal to 2 times something, and A has to be equal to 6 times something. Right? So it means 2 has to divide A, and 6 has to divide A, right? So what's the smallest thing divisible by both 2 and 6? It's got a name, right? The LCM, right?
Yeah,
of 2 and 6.
Least common multiple.
Right?
12.
Which in this case is 6, right?
6.
So
Right,
this is the LCM. I mean, this is basically the LCM of I and J, right? That's sort of the abstraction to, to numbers, but it's the LCM of 2 and 6. Now that's 6, right? So in particular, right? So if I look at this, so 2 intersects 6 is the ideal, which is actually just the LCM, which is just 6, right? What is 2 times 6?
Wow.
So it's this ideal, 12, right? And that's a proper ideal of 6, right? They're not the same. Right. So this is a good example. Again, remember I was telling you Z is a good thing to keep in mind. So here 2 times 6 is strictly contained in 2 intersect 6. Right. And now it's good to just keep in mind this is the LCM. Right. This is 12Z, right? That's that. What do you think 2 plus 6 is? So we're looking at things of the form, so A is in 2 plus 6. If and only if A equals 2x plus 6y. That should look familiar. Looks like Bezo's theorem, yeah. Right? Okay, so when I add two ideals like this, I'm getting the GCD. Right? So these are good to keep in mind, right? So it's good to keep in mind the way ideals in Z work, right? Just to keep in mind more general things, right? Okay, so intersecting two ideals sort of behaves like the LCM. Adding two ideals kind of acts like the GCD, right? When are two, so what happens here? When I do 2 plus 3, what happens? So these two things are relatively prime now, right?
Yes.
So this is gonna, so what's the GCD? That's 1. What's the ideal generated by 1? What is 1Z?
It's all those
That's
things.
It's everything, right?
Yeah.
Okay. Now these, so those two things are relatively prime. We may call those two ideals relatively prime, right? So this is a definition we make. So I, J, subset of R, and again, this will be a ring with unity and commutative, just to keep things easy, right? So I and J are relatively prime. If and only if I plus J equals R, right? So that's in R is, since we're assuming that R has a unit in it, that's the same as saying it's the, generated by 1, right? So this will be if and only if 1 is an element of I plus J. If and only if 1 equals, R times A plus S times B, where R and S is an R, and A is an I, and B is in J, right? So this is sort of a ring version of the Bezout, right? So now there's nothing to prove. This is just all falling out of definitions. Okay, so you say two ideals are relatively prime if the sum, the smallest ideal containing both, right, is actually the entire ring, right? So that's when you say two ideals are relatively prime. Okay. I'm not going to go into this section because we don't need it too much. Okay, there's some algebra of ideals. I sort of talk about. They do have some basic algebra, like I plus J and J plus I are the same. If the ring isn't commutative, IJ and JI generally are not the same, so you have to be careful about that. They do associate. I plus J plus K is I plus J plus K. When you multiply, they associate, right? There is an additive identity for ideals, namely the zero ideal. This is an ideal, right? The singleton zero is an ideal, right? There's a kind of distributivity of ideals. This is true. It's a good exercise to prove that. It's not quite true with intersections. So there's lots of stuff you can say here. We don't need all this. I'm not going to go through it all. These are good exercises for you to practice doing proofs about ideals, right? Like if you want to do some proofs on ideals, there's some good exercises. The relatively prime I talked about, so let me just keep going. Where do I do? Oh yeah, this is the Chinese remainder theorem. So I'm not going to talk about this right now. If I need it, I'll talk about it. But it uses this notion of relative primeness, right? So I'll just say it, and let me say it for Z, and let me say it here. Okay, so in Z, if I have some numbers N1 through Nk, which are pairwise relatively prime. No, what do I want to say? Is that what I want to say? Sorry, now I got to think for a second. I think that's what I want to say. Pairwise, relatively prime. Actually, let me cheat and let me just make sure that's what I want to say. So I got to find where I say it here, actually. Yeah, pairwise relative prime. Then what you get is you get Z, and you take N to be the product. All right, so that's the product. Then you get a homomorphism. In fact, you get a isomorphism. Zn onto Zn1 cross Znk. And it's actually important to know what the homomorphism is. You just take N and you map it to N mod N1, N mod N2, N mod Nk. Right? So if I want to map, for example, Z, let's see, in your test you had like 1, 2, 8, 7, right? And I want to map it to, and you guys all did this. It's Z9 cross Z11 cross Z13, right? That's how those factored, right? So these are mutually relatively prime numbers, right? Then the mapping is just n gets mapped to n mod 9, n mod 11, n mod 11, n mod 13. And you show that this is one-to-one and onto. The onto part's the part that's tricky, right? That's where you have to actually prove something. So if you look at the proof here, I have a proof of that. And we've actually done it before, so I don't want to redo it right now. I don't want to spend too much time on it either. But that's how it works for integers, right? For rings, right? When I'm in a ring and I've got ideals, which are mutually relatively prime. So that's the same theorem essentially. Then what you do is you map R mod the product ideal isomorphic to R mod I1, R mod I2, IK, right? And the mapping is again, well, now it's not some n, right? It's going to be R maps to R plus, right? What is the corresponding ideal thing? R plus I1, right? R plus IK, but not big R, little r. Right? Well, so it's, yeah, I mean, it's really R plus this thing. It's in this thing, right? So if you want to be really careful, it's like R plus I1 IK to that. So it's essentially exactly the same theorem, just for arbitrary ideals using the notion of relative prime that I gave you up there. So again, what does relative prime mean? It means that I plus ij equals R for I not equal to j. Okay. And the proof is exactly the same as the proof for the integers. Okay. At any rate, we won't need it too much. We probably won't need it at all, but it's here, right? So it's in this section. So I'm saying there's some interesting stuff here, but it's not something you're going to need too much. So you don't really need it too much. Is that okay? Is that fair? I mean, we're going to run out of time if I say everything. Okay.
Keep it moving.
Keep it moving. Okay. The next section is really important. So prime ideals and maximal ideals, right? And again, I think most of you know this. This is even really from last week. What is a prime ideal? I have R, right? What does it mean to say I subset of R is prime? So you guys all probably know one definition. So what is the definition you know? Let me get this out of you. I know some of you know, because some of you did some stuff on this already. Someone say something. What does it mean to say an ideal is prime?
That either like in it's a commutative ring, and when you multiply A and B, which are both in that ring, either A or B are in the prime ideal. Is that what it is?
Okay, so you didn't quite get it right, but close. And yeah, I'm gonna go ahead and just assume from now on, I'm going to assume everything's commutative and with a unit. Okay, so let's just make that a standing assumption to keep things simpler. All right, so the notes aren't like that, but for here, let's just do that, right? So it's A, B is in I, implies A is in I, or B is in I. That's what it means to say I is a prime ideal, right? So if a product is in there, then one or the other thing is in there. Now it's equivalent. And again, this is a good exercise. So I'm going to leave it as an exercise to saying that if JK, these are both ideals, is contained in I, right, then J is contained in I, or K is contained in I. Yeah, and you want to kind of think of J contained in I, kind of think of this like I divides J, right? So let's see kind of why that's true using what we have with integers, right? So when is it the case that the ideal n is contained in the ideal m? Now this is in, so R equals Z. Again, think a lot about this ring because this is an important one.
It's modular at that point, isn't it?
No, I'm just asking this question. What is the relationship between n and m if to say that the ideal generated by n, so this is the, by the way, right, this is the same as nz, this is the same as mz. All right, so I'm saying containment is in that direction. So what does that mean?
M is the N divides, I mean, M divides N.
M divides
N
n, yes.
Yes.
Right, so it's almost like inverting, right? So you almost think of m dividing n as being smaller, right? But in terms of the ideals, right, it's kind of turning it around, right? So if you think about the ideals lattice structure, right? What are the ideals? So let's see. Way up at the top, you have 1, which is the entire ring Z, right? What are the things that are just below 1 in size? Where there's nothing in between.
The even and odd number?
Not even and odd, but primes. These are the things which are just.
Oh, coach, we're talking about size now. We're using that for size. Okay, yeah.
Well, it's containment, right? It's containment, right? What is down here below 2 and 3? Well, 6, right? So if you look at the lattice of ideals in Z, right, you get sort of the multiplicative structure of the integers, right? So this is a good kind of picture, but keep in mind it's kind of inverted from what you usually think, right? You usually think of division, you usually think of going down to the primes, right? So your lattice is usually aimed that direction instead of this direction, right? So it's a good thing to keep in mind, right? That containment of ideals is like divisibility in the opposite direction, right? So that's what I meant up here. Saying that J is contained in I is kind of like saying I divides J. So this, you can kind of think of this as saying I divides JK implies I divides J or I divides K, right? Which is how we'd usually think of primes, right? So you want to keep in mind that this direction, sort of natural direction here gets inverted, right? So N is contained in M if and only if M divides N, right? I mean, even the side in which you write this on changes, right? Okay, so keep that in mind. Yeah, when is it ideal of, again, sticking with Z, right? And I've got I an ideal of Z. When is an ideal of Z prime? Make a guess.
Is it if it contains the maximal ideal?
No. It's Z, right? Do we have some other notion of prime in Z? So if and only if I is prime.
Divided by P. Go ahead,
If only if I equals
if and only
P.
if the prime is equal to 0, if n is equal to 0.
If P is prime?
Yeah, an ideal is prime if and only if it's the principal ideal of P for some prime number P, right? That's when you have a prime ideal in Z, right? Actually, let me come back to this in a minute because I want to talk about some more structure of Z because we need that when we get into, I mean, the next thing we're going to look at is like FXs, right? And the structure of these are a lot like Z. So we need to really sort of understand what's going on in Z. But I don't want to leave this topic right here, which is prime and maximal ideals. Let me come back to this real quick. So here's a theorem. I mean, according to the reading quiz, most of you know this. I subset of R, and again, I'm going to just assume commutativity and with 1, right, is prime. You don't need it, but I'm going to assume it here. If and only if R mod I is what? You all did the quiz, and I think almost everyone got this right. So
Can you repeat the question? I think we're a lot of us are just overwhelmed with everything that we've learned, that even basic things that we usually know is just kind of
I mean, this is
glazing over
new.
everything.
This is new, but so I is a prime ideal if and only if the quotient is what?
Z divided by PZ?
No, I mean,
Irreducible.
wait, did
A
someone
I'm
say it?
guessing.
Not a field,
Irreducible.
not irreducible,
Oh.
not quite a field. Let me put it that way. So what's not quite a field?
Integral domain.
Integral domain. Right? So I is a prime ideal if and if R mod I is an integral domain, right? Let's just see why this is true, right? Okay, so there'll be two, like suppose I is a prime ideal. So suppose I is prime. Let's see that R mod I is an integral domain. So suppose we want to show there's no zero divisors, right? So suppose A plus I, B plus I equals, what is zero? It's just I, right? Remember, I is playing the role of zero. Zero plus I, but just I, right? So what is this? How do we define that in terms of cosets? What is A plus I times B plus I? This is the whole reason.
Is it AB plus I?
AB plus I, right?
Plus I,
So
yes.
AB plus I is equal to I. And so what does that really mean? It means that if these two are the same, it really means AB is
Equals 0?
not equal to 0 because all of I is now 0. That's kind of the idea, right? So we do this R mod I, the new 0 is all of I. So we just want to say AB is in I, right? Okay, so remember, A plus I, this is from group theory again, equals B plus I, if and only if A minus B is in I, right? That was just like normal groups. So we're using the additive notation now, right? But now here we have addition and multiplication, right? But this coset is in I if and only if AB is in I. But I is prime, right? So if AB is in I, what does that mean?
That AB is prime.
Well, so we're assuming I is prime, right? The definition of prime was that if AB is an I, then A is an I or B is an I, right? So AB is an I.
One of them has to be one.
A is
so
prime.
not one, zero, right? A is an I or B is an I.
B is an I.
Right, but that means either A plus I equals 0 plus I, right, equals 0 in the quotient, or B plus I equals 0 plus I. So again, equals 0 in the quotient, right? So what that says is it says A plus I, we're assuming that I is prime, right? So A plus I times B plus I equals 0, in the quotient structure, if and only if A, plus I equals 0 or B plus I equals 0. I'm using the 0 bar. I mean, 0 bar is really just I, right? I'm just trying to make it clear that the point is when we do the quotienting out, everything in the ideal becomes 0. That's what we're doing. That's what quotienting out by an ideal does. It takes everything in that ideal and makes it 0, right? That's what it does. Right? It's giving you the new 0. Right? But that tells me that R mod I is an integral domain. I mean, it tells me there's no 0 divisors, right? The rest is because we were assuming that R was commutative and stuff, right? Okay.
So Dr. K, if we made that into like a polynomial structure, would that also be an integral domain?
No, we're not doing that yet. So I don't want to quite say that because I'm not sure exactly what you mean, but I do want to finish this proof, right? So all this says is for any ring R, if I take a prime ideal subset of the ring, our mod I is an integral domain, right? And I want to see the other, I want you to understand why these two directions are true, right? So where do we use prime? We use it right here, right? And we use it immediately to get that if AB plus I is 0, which is what this means, then A is 0 or B is 0, which are what those mean, right? You need to be able to take that and translate it to those other two statements, right? So this basically says AB equals 0, right, in the quotient structure. This says A equals 0 or B equals 0, right? And that's what it means to be an integral domain, is that if a product is 0, then one or the other things have to be 0, right? And let's go the other direction, right? So now if R mod I is an integral domain, I really want you all to look through these proofs and make sure you understand, especially these two proofs.
That means that's the second line right below that. Then that would mean it would be A plus I is equal to 0 plus 1, or 0 plus I, or
no, let's not jump ahead. Let's just say what integral domain is. What does it mean to say R mod I is an integral domain? It means that if
there are no 0 divisors, right?
Right. So if A plus I, B plus I is 0, so that's just I, right? Then A plus I is 0, so that's I, or B plus I is 0, which again is just I, right? So now let me just take that sentence, right? What does this mean? So let me write it a different way. If AB plus I, because that's the same as that, equals I, right? Then A plus I equals I,
or B
plus I equals I.
Equals I.
Okay, but let's rewrite that. This just says if AB is in I, because that's what this means, then A is in I,
or B is in
I. But that says I is prime, right? That's exactly what being prime means. Right? So it should be really clear how one thing leads to another here, and up here how one thing leads to another up there too, right? You really want to kind of get that in your head as being clear so you can see this relationship. Now the thing you want to remember is that R mod I is an integral domain. Actually, I'm just going to say domain. Okay, is a domain. Can I do that so I don't have to write so much? If and only if I is prime. Okay. So now we want what happens with maximal ideals. Okay, so when is an ideal maximal? I subset of R is maximal. And it means basically the only thing it can, if and only if there is no ideal J such that I is contained in J strictly, and this is strictly contained in R. So in other words, if it's just sort of the biggest thing in that lattice substructure, right? So I've got R and I've got I, and there's nothing in between there. That's what it's saying, right? In sort of the lattices of ideals, the lattice of ideals.
Dr. K,
yep.
Just to make sure, this doesn't mean that the maximal ideal is unique, right?
No. Yep. No, no, again, think about Z, right? So it turns out, we'll see this in a minute, but it turns out we have all these primes here. So all of these are prime ideals, but they also all turn out to be maximal ideals, right? So it's important to keep this picture in mind, just to have that as a thing to hold on to, okay? Let's see, so the claim here is I is a maximal ideal. If and only if what? See if someone can guess it.
If everything is prime?
Well, no, R mod I. So it's going to be about R mod I again. Is a what's better than an integral domain?
Field?
Field. Right. So let's prove that, because that sort of tells you a lot about maximal ideals. So suppose I is maximal. God, I wish I could meet with you for 3 times this week. Show R mod I is a field. So this requires just, this particular part requires just a little bit of work. Oh, someone's jumping back in. Okay, so what I want to do, I want to show it's a field. So I'm assuming it's maximal. I want to show it's a field, right? So I want to take an A plus I, right, in R mod I. Right, I want to show it's a field. So what do I need to show? What does it mean for R mod I to be a field?
It has unity and 0 divisors.
Inverse.
No 0 divisors.
Inverse.
So yeah, so a field has to have inverses, right? And definitely can't have 0 divisors, and because it has inverses, it's got to have a unity, right? Again, just to keep things a little bit simpler, for at least in class, let's say that all the rings I'm looking at are unitary, so they have a unit, and are commutative, right? Just to keep that extra layer of stuff out of the way for a second. Okay, so I need to show there is a B such that now I don't get 0, I get 1 plus I, right? I need to show that. All right, because that's what it would mean to have a multiplicative inverse, right? Okay. So I only want A's, and by the way, I only want A's not in I, right? So that's an important thing too, right? I want an A not in I, right? Okay, so here's the deal, right? I could define this principal ideal from A, right? I have an A, which is not in I. I have this principal ideal A. And what I know is I know that if I add I to it, this gives me another ideal, right? J. And we did this adding of ideals before, just something in here plus something in there, right? This is literally things of the form RA plus B, where R is in R and B is in I. Right?
This is something new from something old video.
That's where I'm getting new, where we're constructing things, right? But what do I know about this J? So first of all, is it true that I is a proper subset of J? Is A in J, right? A is in J, right?
Yes.
Because remember, this thing here is also the same as the smallest ideal generated by these two sets, right? So yeah, A is definitely in J, right? If I want, I could say, 1 times A plus 0, right? So that's in J, right? Now I was maximal, so what do I know about J? This is an ideal strictly bigger than I, so what do I know about J?
J is the maximal?
No, I was already maximal. That's what we're assuming, right? We're assuming I is maximal.
Then J has to equal I.
J has to equal R, right? I mean, no, I took something not in I, right? J definitely contains something not in I, right? So it's strictly bigger than I, right? But there's no room for it to go. It has to be all of R, right? But what does that mean? It means that A plus I is equal to R, right? And something that's in R is 1. So it means that AR plus B equals 1 for some R in R, right? Because 1 is in here, right? I mean, 1 is in there, right? So 1 has to be in there, and so it's got to be of that form, right? But what does that mean? That means A plus I, R plus I equals 1 plus I. right? Which is just, R, right? It's everything. But this means that these are multiplicative inverses, right? So this R plus I is a plus I inverse, in R mod I. All right, so we got that if I is maximal, implies R mod I is a field. What about the other direction? Assume R mod I is a field. Can I show that I is maximal? Can I have I contained strictly in J contained strictly in R? And the idea should be kind of clear from what we just did. Like, if I had such a J, right, what can I do? Can I choose something in J which is not in I?
A.
So I can choose some A. Right now I'm assuming R minus I is a field, right? So I'm taking an A which is in J minus I, right? So it's something in J which is not in I, right? And I can look at A plus I inverse, right? I have that thing because I'm in a field, right? I'm assuming this is a field, right? So this is A plus I, B plus I, and where this has the property, so this is A, B plus I, or this is 1 plus I, right? Which is just R again, right? So this is telling me, right, that A, B plus something in I, what I want to write, C, right, is equal to 1, right? Where C is an element of I. Let's see, now what do I want to do? So I'm trying to show that this is maximal. I want to show J has to be all of R. So I want to do. I think I left out a little step here. I think I want to say up here. No, wait, I'm taking something in J. Oh, wait. Sorry. Maybe, yeah, okay, sorry. Yeah, let me try doing this sort of by contradiction. Okay, so let me suppose this, right? Suppose that I have strict subset, right? So suppose I have this a field, suppose it's not maximal. I guess that's what I'm doing, right? Suppose this is not maximal. I take my A and J minus I. And then I want to see that I don't have a field. Yeah, I guess I want to get a contradiction. Yep, sorry. Let me back all this up. I'm probably undoing something I don't need to undo. So let me back up. So let me suppose I had. I want to show I is maximal, right? So I want to take. Okay, let me just start over. Okay, I'm just going to start over here. R mod I is a field. Okay, I want to show I is maximal. So I'm going to take R no, I'm going to take A and R minus I. And I want to show that A plus I, because this would be the smallest ideal bigger than I containing A, has to already be all of R, right? So that's what I want to show. If that's true, then I is maximal. Otherwise, I could get a J in between, right? If I could get something like this, right, then I could take A to be inside of J and I wouldn't get this, right? So I want to show that I get A plus I equals R. That's what I want to show. So let me see if I can do that. So I get A plus I times B plus I is equal to R, right? I get that because this is the inverse, right? This is A plus I inverse. All right, so this is saying A, B plus I is equal to R, right? And so A, B, this looks plus C is equal to 1. So this is kind of like what I had before. C is an I, right? Oh, wait, I don't have to do anything. I mean, no, sorry, I get this, right? A, B plus C is equal to I. So that tells me, sorry, it's equal to 1, right? In fact, I get this. Yeah, I'm sorry, I'm overcomplicating things, right? I get that just from there, right? But yeah, okay, but A, B is certainly an element of A, right? So because I mean, this is just everything in R times A, right? That's what I mean. That's what A, B, right? A is AR. It's the principal ideal, so it certainly contains AB, right? So in particular, A plus I is equal to R, right? Just from this, right? I didn't need to go any further, just from that. So because I have an inverse, right? I get this, and that gives me that, right? But this already gives me that has to be R, right? Which means there's no J in between I and R, right? So it is a maximal ideal, right? So I is maximal.
I thought you were trying to prove that J is R.
I backtracked. I mean, I changed my mind. So yeah. So let me just rephrase. So what I did here is I'm assuming this is a field, right?
Right.
I'm taking. I want to show that I is maximal. That's what I want to do.
I understood everything
right.
that you did, Dr. K. I did, but I was just wondering what was the purpose of saying proving that J was equivalent to R. That's what I was just trying to understand.
Well, that's why I erased all that because I changed the way I'm doing it, right? So I'm just taking an A which is in R minus I. So I'm taking something which is not in I, right? And I'm wanting to show that when I adjoin A to I, if I look at the smallest ideal with A and I have to get R, and that tells me that there's nothing in between. There's no room in between, right? I mean, if I had R here and I had I here and I had some room for ideals in there, right? Then I would be able to find one like that, right? Because I just take something inside there, right? But what we're showing is that there is no room for ideals in there because once I take something in there, I come up with this guy, but this guy is already in there, right? But this is already giving me all of R, right?
Right.
So yeah, so in other words, this doesn't exist. There's no space in between those. That's what it's saying in terms of the ideals, right? So together, right, we have prime if and only if R mod I is integral domain. Field if and only if R mod I, try that again, maximal I prime, I maximal, if and only if R mod I is a field. Notice that if we're a field, we're definitely an integral domain, right?
Mm-hmm.
So maximal implies prime, right? So we're also getting that, right? Any maximal ideal is prime. Okay. In general, it's not true that all prime ideals are maximal. It is true in Z that all prime ideals are maximal. Okay, so we're going to see why that's true. Unfortunately, probably not tonight. Okay, I've got 4 minutes. Let me say some important things about Z, and I'll have to pretty much start here next time. Z has the Euclidean division algorithm, right? So in Z, given an n in Z, right? We can take some m and write it as qn plus r, right? Where r is the remainder. And that's what allows us to do all sorts of stuff in number theory, right? But one thing it does here is it tells us in Z, every ideal is principal. So let's just prove this, and we'll stop there. But this is going to be one of the key things that we look at f of x's. This will also be true there. Take an ideal. Okay, I can let n equal the least a and I, such that a is greater than 0. Right? Why can I do that? Because if I look at the set of all a and I, such that a is greater than 0, take it to be a non-trivial ideal, right? So not equal to 0, right? Is this non-empty? So there's something in the ideal. It's an integer, right? The ideal is a group, so it's closed under minus sign, right? So if I pick something that's negative, I definitely get something that's positive, right? So I definitely have some positive things in the ideal, right? So this is a non-empty set of positive numbers, right? And so it has a least element. That's induction or the minimal member principle or well-ordering principle, whatever you want to call it, right? But there is a least element of I, right? And I want to claim, and I want you to understand this proof because this is what we're going to repeat for the polynomials, is that I just is in. Right, so that's what I want to show. So suppose m is in I. Right, what can I do? Well, I can use my, algorithm up there, right? And I can say m is equal to qn plus r, right? So r is equal to m minus qn. Oh, and by the way we do this, right, is this, when we do this, right, we always make sure this qn is less, we always make sure this qn is less than m, less than the absolute value of m, right? I mean, that's part of what we do when we do this Euclidean algorithm, right? Or maybe I just want to say m, I don't know. I can choose a positive, so let it be positive, right? So everything here is positive, so that's true, okay? But where is this thing here? Where does m live?
In I.
M is in I. Where does n live? It's definitely in I. That's how we chose it, right?
Mm-hmm.
So where is qn? Well, it's definitely in I because I is closed under multiplication by anything, right? So this guy here is an I, right? Because m is an I and qn is an I. Remember, this remainder is always greater than or equal to 0, right?
Isn't this just the Chinese mod? Isn't this just Chinese both the modular dividend modular stuff?
Yeah, this is just the modular stuff. This is, but it's just the Euclidean division algorithm, right? What can I conclude about R, right? So R is an I. R is an I. R is less than N, right? That's part of how we choose the remainder, right? And dividing by N.
Mm-hmm.
Okay. But what was N? And R is greater than or equal to 0, right? So what's the only option for R here? Can it be greater than 0?
Yes.
No, it can't be greater than 0, right? Because if it were greater than 0, then R would have been what I chose.
Where did you point at? I just said, I was back at the point where you said what R is less than N, but R is also greater than 0. That's what you just said. I wasn't looking up.
So N is the least thing in I, which is greater than 0. The very least thing in I greater than 0. R is in I, and it's less than N, right? And it's greater than or equal to 0, right? So the only thing R can possibly be is 0, right? So what we actually, so R must equal 0. And what does that mean? It means M must equal Qn. All right. And what that means is it means I took an M element of I.
So we just proved R is divided by I.
Well, not R, but M. I proved that N divides M. Right? By taking the least, I mean, all I had to do was take the least positive thing in I, call that N, and I take anything else in M, in I, and I show that N has to divide M. Right? That's what we just showed. All right. But what does that mean? It means, well, it means among other things that I is contained in N, right? But N is an element of I, so it must also contain I, right? I mean, you know, if N is an element of an ideal, then the principal ideal generated by N is also in there, right? So I get that. So in fact, N has to equal I.
That makes more sense. I get that.
Right? So the only ideals in Z are principal ideals. Okay, so Z is called a principal ideal domain. It'll turn out that Fx's, where F is a field, are principal ideal domains. And there's a kind of Euclidean division algorithm for those. So we'll prove this in exactly the same way. Principal ideal domains have lots and lots and lots of really nice properties. For example, every prime ideal is maximal, right? So as soon as I know an ideal is prime, I know that when I form the quotient structure, I get a field, right? So we're gonna look at all that stuff, I guess, next week. Lots of stuff, right? Too much. I see the dog. Okay, anyway, I'm gonna stop there. Any questions about this so far? Any last minute, like I gotta see something or other, or are you dying to see something? Anyone who wants to leave can leave. Anyone who wants to ask a question can stay and ask a question.
Oh, you know, I'm sure I'll have a million as I'm doing the work, but right now none come to mind.
You know, it's amazing you guys say that, but then I don't get a million questions during the week. So I mean, you can send me questions.
So we're like, no, do it.
Chapter 17 was a lot easier than chapter 16, probably because it was just a lot of algebra. But that's why I asked what I asked at the beginning of the class. Chapter 16 was a lot of proofs with theories, but in chapter 17 we just get to do a lot of math.
There's a big mix. Yeah, there's a big mix for the rest of the. We really got. I mean, let's pretend 17 really wasn't touched yet. So we really got 17, 18, and 19. There's a lot of computation there.
Yeah.
But it does use a lot of the theory. I mean, you got to know when you're in a unique factorization domain, when you've got primes, when you've got irreducibles. And so a lot of the theory is used along the way in the computations. I guess that's the thing, right? You've got to know the theory in order to do the computations for that stuff. So that's the tricky part.
What about number 35 on chapter 16? Because that word every field is giving me every time. I don't understand how it's.
Let's see.
That polynomial is touching for every field, and I'm stuck on that problem.
So it's 35 on chapter 17 or 16?
I think
16, 35.
And I think the word that's getting me is saying every. So,
but it's on MAT-3.
Oh, okay. So okay. So let's see. So the question is, x don't, let's see, 35, x cubed minus 2x squared minus 9. So this is fx. And we want to show that, yeah, we want to show that f has a root in every field. And let's just say, I guess one thing to say about why this makes sense, why can we even make sense of 1, 2, and 9, right? In every field, we kind of talked about this a little bit last time, right? We can always map Z into a ring, right? And there's kind of this copy of Z or Z mod N or whatever inside that ring, right? Depending on the characteristic of the ring. So in this case, the field. So I mean, these coefficients you can think about as being coefficients in an arbitrary field, even though they look like they're integers, right? So I mean, this may be Z2, in which case this would be 0, right? And this 9 would be 1, right? For example, right? So I mean, that kind of thing can happen. So when you're talking about every field and you're looking at these things that appear to be numbers, you want to think about the copy of those numbers in those fields, right? So just bear that in mind. So what this 2 means and what this 9 means may depend on what field you're in, right? So keep that in mind. And let's see, I think the point here, what happens if I compute f of 3? And then I get 3 cubed minus 2 times 3 squared minus 3 times 3, right? And so that's 0, right? I think that's all I have to do. I mean, yeah, so don't forget doing normal algebra, right? Because I mean, all I did is I evaluated at 3, right? And we can do normal algebra here. So this is minus 3 times 3 squared, right? I'm not, now these things may be 0, I don't know, whatever they are, right? But this is 3 cubed minus 3 cubed, which is 0, no matter what. No matter what 3 is, even if this is in Z2, where 3 is 1, this algebra still holds, right? So here you're just using the fact that you can eyeball a root, more or less, right? This came up last week where you were doing some sort of, people were wanting to, and I didn't get to talk about this as much as I wanted to. There was one you did like this, I think, right? And people were using quadratic formula and stuff, and this was over arbitrary fields, right? Maybe just arbitrary fields. I don't remember exactly what the situation was. But you're wanting to use quadratic formula. Now, you got to be really careful with quadratic formula because there's all sorts of things that can go wrong, right? Because there you've got square root, you've got, you know, minus b plus or minus square root of b squared, so minus 5 squared, minus 4 times 1 times 6 over 2, right? But what do you need to make this work? You need 1 over 2 for one thing, right? And then you need like the square root of whatever this is, square root of the discriminant for another, right? So this doesn't work in all fields, right? So you got to be careful about doing stuff like this. But on the other hand, this thing does factor, right? I mean, don't forget to do stuff like this. And this is always true, right? I mean, don't forget the easy stuff while you're doing the hard stuff. I haven't, not even looking at the window anymore. There are still people there. Okay, right. So I mean, don't forget using your standard normal algebra stuff while you're doing the more complicated stuff. All right. Did that kind of answer that one? I mean, what 3 is?
Yes, it does. I had that right there, but I just when I'm thinking about every field, what is? I don't know. I don't know. Well, I don't.
So the only field. So the only field not covered, obviously, here is one that doesn't have a 3, right? So I guess Z3 and Z2, or if you like, fields where the characteristic of F is 3 or 2 is a little bit weird here. But if you just translate this problem in, I mean, what we did doesn't matter what 3 is, right? So, you know, in say if it's in Z2, right, then this 3 just becomes a 1, right? That becomes a 0, and these just become 1s, but it still all works, right? I mean, so the point is anything you do that's just using, you know, associativity, you know, divisibility, you know, any of the field axioms, right? Anything you do works, right? And you know, the issue here is you got to interpret this like, so it is an interesting question. So this fx, x cubed minus 2x squared minus 9, these are really integers, right? Those are powers of the variable x, right? But these are kind of like copies of those things inside the field, right? So if my field happens to be Z2, right, then this thing just turns into x cubed. That just becomes 0, and this becomes minus 1, right? And if I'm working in Z3, what ends up happening here is this is x cubed. This is now minus 2x squared, and this is now 0 there, right? So that becomes 0, right? In Z3, right? And minus 2 in Z3 is just the same as 1, so this is the same as x cubed plus x squared, right? In Z3, right? Because minus 2 is equal to 1. I mean, it's kind of fun doing this stuff, I think, right? And so then obviously you've got 0 and like minus 1 as a root, right? So yeah, I mean, and let's see how that, right? So here I have x squared times x plus 1, right? So here I have minus 1 as a root, but up here I said I had 3 as a root, right? But 3 is the same as, oh no, sorry, 0, right? So 0, I have 0 in that, but 0, 3 is the same as 0 in this case, right? Anyway, you can kind of play with it, right? So the only trick there is in sort of how to interpret these things inside the field as whatever they are. Those things are literally powers. I mean, that literally just means 3 copies of x, right? So that 3 isn't inside the field. That 3 is in the real universe where we're taking powers. All right, so that's a place where you have to be a little bit careful because we have different copies of Z laying around all over the place.
Thank you,
Right.
Dr. K.
Sure. Any other questions before I bid you farewell for the week?
Good night, everyone.
Okay, see you guys. Bye-bye.